This is Thermochemistry 3, and it is on calorimetry. First, let's define heat. Heat, which will be denoted with a lowercase q, is the change of thermal energy between a system and its surroundings. It's the energy that is transferred from one object to another due to a difference in temperature. It has a very specific definition in this unit as heat is Q, and I'm going to go into several equations that we're going to be using, but it is critical to distinguish heat, lowercase q, from enthalpy, which is a delta capital H. So keep that in mind as we work through this particular video, that you want to make sure you can distinguish between the two. So let's get started by looking at this schematic, which is a review of the last couple podcasts. So here we have our system within a flask, and we're showing that heat is given off or produced, okay? Heat is given off or produced. When that occurs, we get a delta H, or an enthalpy of reaction, that is less than 0. So we get a negative delta H value, indicative of an exothermic reaction in which heat is given off to the surroundings from the system. Here we have a graph that's showing the system before, and then it is in a lower energy state after. Where did the energy go? It went to the surroundings. On the right side, we have an endothermic reaction, which has a delta H, or enthalpy of reaction value greater than 0. So we have a positive enthalpy value. We see the system before is low energy, and after it is at a higher energy level. So heat energy was absorbed, and that is indicated thermochemically in an equation as a reactant for an endothermic reaction. Two definitions here that are often confused, but that are very different. Heat capacity, a capital C, is the amount of energy needed to raise the temperature of an object or a substance 1 degree Celsius, and the units are in joules per degree Celsius. Now, I've asked you throughout this video to keep in mind or try to distinguish between heat and enthalpy. Well, here's one important fact that I want you to make note of. Heat is indicated in the units of joules. Heat units joules, whereas enthalpy was in kilojoules, and not only that, it was in kilojoules per mole. It was an extensive property dependent on the amount of substance. So that would be the first thing I would really make note of, is that change in enthalpy is kilojoules per mole, whereas heat and heat capacity and specific heat capacity, which I'll define in a moment, are expressed in terms of the joule. So there are 1,000 joules in 1 kilojoule, and that is one mistake that is often made in this unit. Specific heat capacity is the amount of energy required to increase the temperature 1 degree Celsius for an object, and more specifically, 1 gram of that substance. So our units are joules per gram degree Celsius, and that is very important. And we will be using specific heat capacity in our upcoming calculations. And specific heat capacity is denoted with a lowercase c. So we have 4 variables here we're discussing all at once. Heat, which is a lowercase q. Some textbooks will indicate it as an uppercase q. and it really doesn't matter, but the overall consensus among chemists would be to use a lowercase q for heat. We have a delta capital H, which is in kilojoules per mole. We have heat capacity, which is capital C. Then we have specific heat capacity, lowercase c, and not to confuse you even more, but oftentimes specific heat capacity will be referred to as specific heat. So think of that word specific because you're specifying the amount of the substance to be 1 gram. Let's look at some compounds here and really look at the specific heat capacity of liquid water and just compare these values and think about what these values indicate. Again, the amount of energy in joules to raise 1 gram of the substance 1 degree Celsius. Look how high liquid water is on this scale, relatively speaking. So you've learned so much about water, whether it was last year in biology, the properties of life, whether it was earlier this year looking at the intermolecular forces, hydrogen bonding. But this all supports this idea because of the energy required to heat up water. Relatively speaking, it's considerably higher than these other substances. Now, if you're wondering about the phases of water, whether a solid, liquid, or a gas, that's coming up in a podcast here within this unit. So I just wanted to show you this. We're going to use 4.84. 4.8 is also used, but very common in this unit. And you'll actually memorize this because we use it so often. 4.184 joules per gram degrees Celsius. All right. So calorimetry is a technique that can be used to measure the amount of heat that is released from a system or absorbed into a system during a chemical reaction. It can also be used to look at heat released and absorbed involved in a physical change. The name of this device is a calorimeter. So we're going to be doing several labs involving calorimetry. Let's look at a basic calorimeter. So here we have 2 styrofoam cups. They are nested within each other. We have some sort of insulated stopper or lid. What we use in lab is we take a styrofoam cup, cut it in half and invert it, and that becomes our lid. And you would be shocked at how accurate these types of calorimeters are, because there are much fancier versions. In fact, there's something called a bomb calorimeter that can measure heat absorbed and released in a reaction that, say, doesn't involve a liquid substrate. I can show you one of those in class as well. We have a thermometer to monitor the change in temperature. And then in this instance here, there's a rod that's inserted here that can be used to stir the system. All right. And we'll probably just use the thermometer in our lab because we can stir using the thermometer, and that way we're not introducing another object into the system. Okay, Q equals MC delta T. This is the equation that we're going to be using when we look at how heat is measured and how it's actually released and absorbed within a system. So this is our way of quantifying heat released and absorbed. So let's go through the equation. It's very important to understand each part in the units. Q, lowercase q, is heat, and heat will be expressed in the units of joules. Again, remember enthalpy was in kilojoules, all right? Kilojoules per mole, whereas heat, lowercase q, is simply joules. Then we have M, which is the mass of the substance expressed in grams. We have lowercase c. The specific heat capacity, also called the specific heat of a substance, and the units here are joules per gram degrees Celsius. Lastly, we have delta T. Well, delta T is the temperature change, and our temperature is expressed in degrees Celsius. So let's go ahead and look at delta T and really make sure you understand that it is the final temperature minus the initial temperature. That's what we mean by delta T, or change in temperature. Okay, so for any heat calculation that's involving a physical processes, and we're only looking within the system and its surroundings, we're going to use Q equals MC delta T to compare the heat between, say, two objects that are in our system. Remember, we, the scientists, define our system. So the heat lost and the heat gained within a system is zero. It's important for you to think about this. Keep this in the back of your mind throughout our discussion here. So whatever heat is lost by one object is gained by another object. So overall, the summation of those within a system would equal zero. So if heat lost from a hotter substance is gained by a colder substance, this is another way of saying it. Therefore, if we subtract heat loss from both sides of the equation, we can say the heat gained is equal to the negative of the heat lost. Now, as you know by this point in the course, it is important for me to explain to you guys where equations come from and how they're used and why they're used. And so here in a little bit, I'm going to tell you that we're not going to worry about the signage, that we're going to look at the absolute value. But before we go there, I want to show you why I'm going to tell you we're going to only consider absolute values in these computations. So the Q of the cold substance is equal to the negative Q of the hot substance. Now, I think this will become much clearer if we can go ahead and look at a diagram here to compare what's happening. So here we have objects A and B. A and B are brought close together. A and B are now defined as the system. The system is made up of two objects, object A and object B. These two objects are in contact. Object A is hot, object B is relatively cold. When they come together, what happens between A and B is heat is transferred, in thermal energy is transferred from A to B until A and B are the same. So the amount of heat lost from A is gained by B, but overall, that total energy is equal to zero, okay? So we have an equation, Q equals MC delta T for heat, that will allow us to quantify heat absorbed and heat released for a given substance of given mass at given temperatures and with a given specific heat capacity. So this is the overall intuition behind this type of problem that we're going to look at, and we're going to also explore in lab. So let's get to example problem number 1. Inside of a calorimeter, a 30-gram piece of copper pipe, which is initially at 80 degrees Celsius, is placed into 100 grams of water. Now, the water is initially at 27 degrees Celsius, so just a little bit more than room temperature. What is the final temperature of the system? Now, what is our system? Let's define the system as the water and the copper pipe. So what is the final temperature of that two-object system. Assume there is no heat being transferred to the surroundings. Okay, so we're making an assumption here that there's no thermal energy being absorbed by the calorimeter itself. The specific heat capacity of copper, so you must be given that, is 0.385 joules per gram degrees Celsius. So you're given that. And you know water is 4.184 joules per gram degrees Celsius. So we're going to set Q cold equal to Q hot, and I'm going to keep the signage for this particular problem, and you'll find it doesn't matter. Let's lay out our equation. We have our cold, well, that's the Q water, all right? And then we're setting that equal to the negative copper heat, and acknowledging that overall the water plus the copper will sum to 0 because the heat energy lost from the copper is gained by the water until they equilibrate, until the temperature of the system remains constant. And I'm throwing a lot of jargon out at you. It's going to be much easier to understand this when we actually apply these equations in a lab. So, again, cold object, hot object, water is relatively colder than the 80 Celsius pipe. And we're going to put the pipe into the water, into a calorimeter, close the calorimeter with the thermometer inside, and we're going to monitor delta T, or the temperature change of the copper water system. Okay, let's plug in some numbers and look at what this looks like. For water, we have 100 grams of water. We have the specific heat, or specific heat capacity of water, 4.184. And then we have our delta T, our change in temperature, which is always temperature final minus temperature initial. Well, the temperature final is going to be the temperature of the system, and we don't know that yet. We can predict that the overall temperature will go up, but we do know the initial temperature of the water to be 27 degrees Celsius. Now let's look at our piece of copper pipe. We have a 30 grams of copper pipe, and we're given the specific heat capacity for solid copper to be 0.385, and the final temperature we don't know, but we can predict if heat is going to flow from the hotter object to the colder, then the hot copper pipe is going to decrease for its final temperature. But we do know its initial temperature to be 80 degrees Celsius. I love this stuff. This is so cool. All right, so we have everything laid out. Notice the right side of the equation. I've enclosed the entire right side in brackets and included the signage here, this negative sign. Okay, so again, I'm trying to make a point here so that you understand why I'm about to tell you we're going to worry about absolute values when we're using this equation for a system. Okay, now let's do a little algebra. On the left side of the equation, you're going to multiply 100 by 4.81, which is where 4.184.4 comes from. Then you're going to use the distributive property of multiplication. So you're going to multiply the 418.4 times TF. And then including the signage, you're going to multiply the 418.4. You're going to now multiply that times 27. So minus, when you multiply that by 27, you get 11,296.8. If you look at your units, we're unitless here. So go ahead and look at the units because I've always encouraged students to do that. All the units there cancel out on that side. And so now let's do the same thing for the right side. All right, you're going to multiply 30 and 0.385. That's where this negative 11.55 comes from. Distributive property of multiplication, 11.55 multiplied by T final. Note the signage here because this negative sign. And then we have a negative 11.55 multiplied by a negative 80 degrees Celsius, giving us a positive 924, and there are no units there. So we've simplified the expression. Now it's simply a matter of solving for temperature final. So to solve for temperature final, you're going to add 11.55 T final to both sides of the equation. That gets rid of this. That brings the left side to 429.95 T final. You're then going to add 11,296.8 to both sides of the equation, which will bring you to a positive 12,220.8 on the right side of the equation. All of our signage is gone. Dividing both sides by 429.95 gives us our final temperature of 28.4 degrees Celsius with 3 significant digits. Now, did our prediction hold true? Let's look at it. Did the water temperature increase? Yes, it did. It went from 27 to 28.4. Did the pipe temperature decrease? Yes, it did. It went from 80 degrees Celsius to also being 28.4. This is what is so cool. The temperature of the system is the same for final temperature reading. So imagine dropping the pipe in the water and waiting with your calorimeter and monitoring the water copper water system temperature until the temperature held constant. That would be your T final. So it makes sense. For the system, the temperature of the copper pipe is equal to the temperature of the water. If we look at them individually, temperature of the water went up, temperature of the copper went way down. Why did the temperature of the water only go up a little bit relative to the copper? Because water has such a high specific heat capacity of 4.184 compared to a 0.385. So take a minute, pause the video, think about the algebra here, think about how we simplified this equation, but most importantly, think about how we went through the intuition behind what occurred, and we made predictions about what would happen to each object and what would occur to the overall system of this water copper system. Okay. All right. So they are the same in the end. Let's do another practice problem. A brass ball with an initial temperature of 95.55 degrees Celsius. It's placed into an insulated beaker containing 125 milliliters of water. And the water is at 20.50 degrees Celsius. When the two substances reach thermal equilibrium, okay, that's where that temperature no longer is fluctuating. That's where the temperature of the two objects or the system remains constant. Their final temperature is 26.55 degrees Celsius. What's different about this problem already? You're given the final temperature of the system and you're asked, what is the mass of the brass ball bearing? So this is different, but we're still going to employ the same methodology here. A couple of points to make before we delve into the mathematics. Water, the density of water, you've seen this in lab before, is approximately 1 gram per milliliter. So we're going to assume that the density of water is exactly 1 gram per milliliter, because when we're using the equation Q equals MC delta T, it is based on the mass of the substance in grams. And we're given milliliters of the substance. So we need to convert this by simply acknowledging, hey, this is 125 grams of water. Also, I want to bring to your attention the mass, or excuse me, the specific heat capacity for brass. All right. So you will be given this information in any problems that you are asked to solve. In this case, it's 0.380. Wow, that's considerably less than the specific heat capacity of water. Okay, now acknowledging that the Q initial for the water is equal to the Q for the brass ball bearing. We've set those equal. Where'd the signage go? Where'd the negative go? Well, look at how we went into all of those details in example problem 1 to show that ultimately the signage canceled out. So let's put what we know here. We know the grams, 125. We know the specific heat capacity for water. We know the temperature final minus temperature initial. Be careful there. You'll run into problems if you do not use delta T to be final temp minus initial temp. So 2655 minus the initial temp of water. And we're going to set that equal to the quantities for the brass ball bearing. We don't know the mass. That's what we're trying to solve for in the problem. We know the specific heat capacity to be 0.380 joules per gram degrees Celsius. We have the final temperature. Notice it is the same because of the system. That's what thermal equilibrium is, where the two objects which comprise the system reach the same temperature and they stabilize. All right. But we do have that initial temp of the brass ball bearing to be 95.55 degrees Celsius. So what's going to happen to the hotter object? Thermal energy will move to the colder object, which in this case is the water. Okay. So let's rearrange this mathematically. And all I've done here is I am dividing the left side of the equation by these quantities. All right. Just make sure when you're putting things in these values into your calculator, just take the time to make sure the order of operations is done correctly. Make sure you find the delta temperature and then multiply that quantity by the other quantities, etc. Okay, and we can solve for the mass of the brass. And we get a final answer of 121 grams. That is with 3 significant figures because our specific heat capacity that's given for brass is 3 significant figures. So 121 grams is the value we will report for this particular problem. Okay, so I'm only going to do those 2 example problems because we are going to plan and carry out an investigation as is required by the Georgia Standards of Excellence to explore how much heat is absorbed or released in a physical and a chemical process. I'll see you guys in class.